All right, so in this chapter we're going to be talking about stereochemistry. And we've talked about this a little bit in chapter 1. And what stereochemistry is, if you remember, is the 3D structural study of molecules. And some terminology we're going to be using to talk about the 3D nature of molecules are the following. So the first one is chirality. And this is when a carbon has 4 different substituents on it. It's called a chiral carbon. And an enantiomer is when we have 2 different stereoisomers which are not superimposable, so they cannot be perfectly placed on top of one another. And achiral, meaning molecules without a chiral center. So when we're thinking about carbon, right, what's important to note is, right, it has that tetrahedral geometry, right, when carbon is sp3 hybridized. So we have carbon, right, and it has those 4 bonds on it, right? The wedge bond coming towards us and the dashed bond going away, right? Each of these bonds 109.5 degrees apart. And so, an example of methane, there's no difference between these substituents. They're all the same, right? So this is an achiral molecule. However, if we were to take the same exact molecule, or rather the same exact sort of bond structure, right? And now, instead of having all the same substituents, we have different substituents, right? So hydrogen here, CH3 here, bromine here, and chlorine here, right? Now we have 4 different substituents, right? So now this is a chiral carbon. Right? And when we're talking about chirality, we can also think about it as handedness, like a left hand and a right hand. So if we were to take the mirror image of this molecule here and say draw out the other image of it, right, kind of looking at it like we're looking right at a mirror, these are actually different atoms, or different molecules now. It might look like it's in the same, all the bonds are in the same positions, but if we try to turn this molecule onto itself, we'll find that they are no longer superimposable. Okay, so these are enantiomers. Right, they are 2 stereoisomers which are not superimposable. They cannot be perfectly placed on top of one another. And the best way to illustrate that is looking at this image here, right, that's left-handed and right-handed. And we see again that mirror plane going right down the middle. Right, we have these 2 molecules that look the same, right, and if you can imagine, and I'd like you to do this, take your 2 hands and have them in the same position that the screen shows. Right? Now imagine the position of the molecule, right, in all those groups on the same parts of your hands. And now try to take your hands and have the palms of your hands facing towards the screen. Now try taking your left hand and putting it on top of your right. It no longer fits, right? Your thumbs, where those hydrogens are no longer in the same sort of position, right? You can't make them fit on top of each other. If you try to take the palms of your hands and put them together, that's not superimposable, right? They're not really going into each other. You just have them facing each other. But when you try to perfectly put them on top of one another, you'll have issues getting those molecules to be totally superimposable. And this is especially when a model kit's going to come in handy, thinking about molecules in a 3D sense, right? Because you can build out these molecules with this tetrahedral carbon center and see that, yes, they cannot fit on top of one another. You can rotate the molecule all you want, but you can never perfectly superimpose one on top of the other. So in every case where we have a chiral carbon, it'll either be quote-unquote left-handed or right-handed. And so now we have to think about how we can talk about these chiral carbons in a meaningful way. And so what we're going to be looking at now is something called the Kohn-Ingold-Prelog rules, which is just a way for us to determine if a carbon is quote-unquote left-handed or right-handed. And we're going to be doing that through something called R or S configuration. And so what that means is we're going to be assigning priorities to the different groups bonded to a chiral carbon, with 1 being the highest priority and 4 being the lowest priority. Okay? And so when we have a high priority group, that means it has an atom with a higher atomic number. If we have a tie, we use the next atom along the chain as tiebreakers. We have R configuration, where when we number the groups, that numbering goes clockwise. And oppositely, we have S configuration, when 1, 2, 3 goes counterclockwise. Now what's important here is that when we're reviewing the molecule, we need the 4 group to be going away from us on the dash bond. And this might require some rotation of the molecule in order to get that to happen. Okay? And what's important here is just like naming alkanes, R and S configuration, this is not an indication of chemical properties. Okay, this is just how we're naming the carbon. This is just a meaningful way, again, for us to talk about these molecules. So looking at this example here, right, the first thing we have to do when we're trying to determine the configuration of the chiral carbon center, we have to assign priorities to the groups. And so looking at our chiral carbon here, right, we have 4 different groups attached to it. We have a methyl group, an ethyl group, a fluorine, and a hydrogen. Okay? So we have to go through and determine which is the highest priority. Okay? So looking at each of these, we have a fluorine, a carbon, and a hydrogen. So in terms of atomic number, fluorine is the highest priority group. And hydrogen, right, with an atomic number of 1, is our lowest priority. So now we have 2 carbons left. Right? We have a carbon attached to 3 hydrogens, and we have a carbon attached to 2 hydrogens and a carbon. Right? So this is going to be our tiebreaker. Right? Even though they're both carbons, right, this carbon is attached to 1 carbon and 2 hydrogens, and this carbon is attached to 3 hydrogens. Okay? So this is our number 2 priority group, and this is our number 3 priority group. Okay? So now, right, we have our priorities all set, so we have to look at the order of the numbers. We see that it goes counterclockwise. Right, 1, 2, 3. And so that is S configuration. Right, so we know that our carbon here is S. Okay? And so now what about the enantiomer for this molecule? Right, drawing in a mirror plane here, right, we can exactly mirror this molecule now. Right, so we're just drawing the same exact structure, seemingly, except in the opposite way. Or the mirrored way, rather. Right, so upon first glance, these might look like the same molecule, right, but they're not. Right? Fluorine is priority 1, ethyl 2, methyl 3, and hydrogen 4. And when we try to look at the numbering, the priority list, we see that it goes clockwise instead. So this carbon has a configuration of R, right? These are enantiomers. Right? And because a chiral carbon, right, can only be S or R, another way we could draw that enantiomer to make it look more like our original, right, and not just a mirror image, is we can look at it like this. Right, where now the hydrogen is on a wedge and a fluorine is on the dash. Right, see, we've essentially just switched 2 groups. Right, and so this must be the R configuration. And we can prove that to ourselves by numbering it again. So we know that, again, hydrogen is 4, fluorine is 1, methyl is 3, and ethyl is 2, right? But remember, right, the 4 group has to be going away from us, so it has to be on a dash bond. Here it's on a wedge bond, so how do we fix that? And so the way we fix that is by rotating a bond, right? Remembering that sp3 carbons can undergo rotations. So what we have to do is rotate this carbon CH3 bond. Right, and when we do that, right, this bond stays the same. And the general position, right, the wedged, the dash, and the end of the plane bond are also in the same position, but the groups on them are now different, right? Because if we rotate this in the way I have my arrow pointed, right, the hydrogen on the wedge gets pushed this way, and so now it's on the dashed. The fluorine on the dash, right, because we're rotating the molecule around, the fluorine is now in the plane. And the ethyl group, right, rotating this way, is on the wedge. And so hopefully you can see that rotation. It's kind of difficult, of course, to do that sort of mental gymnastics. And again, a model case here would really show this rotation really clearly. Right, so again, looking at these looking at these groups now, right, we have fluorine 1, ethyl 2, ethyl 3, and hydrogen 4. Looking at these positions, right, going from 1 to 3, we have our clockwise configuration. So this carbon is still our configuration, right? So we're going to be doing some practice with rotating bonds and getting good at being able to tell when we have an S versus an R configuration, okay? The way I've shown it is a sort of, you might call it a complicated way to do it by rotating all the bonds, and that mental gymnastics can be difficult. But another way to think about it is, maybe you've already determined this, if you have the lowest priority hydrogen coming towards you on a wedge, instead of doing all the bond rotations, just figure out what the configuration is for this, and then reverse it. Right, so here it seems to be going counterclockwise, which would be S, but because we have a hydrogen on the wedge, we just reverse that. Okay. So before we move on to some examples that we'll do in lecture, I just wanted to point out something kind of important, right? So when we're talking about enantiomers, what's really important to note is that enantiomers have the same physical properties. There's nothing physically different about them, right? Same melting point, boiling point, interaction with non-chiral molecules, and heats of combustion. But what is different about them is optical activity, which we'll talk about in the next video, their odors, sometimes colors, solubility in chiral solvents, so solvents with chiral centers, and reactivity with other chiral molecules, so enzymes. And so in this example I have down here, right, to sort of bring this to a biological aspect, we have an R enantiomer and an S enantiomer. And you can see, right, you don't have groups here, we have sort of shapes, right? And so we can see that these are mirror images of one another, right? These two molecules, right? The S and R enantiomer. And here, down below, we sort of have our, right, enzyme, right? And molecules bind to enzymes. But, right, see, this enzyme has very specific shapes that the enantiomers need to put the groups into, right? So it's sort of like a lock and key situation, right? If the enzyme is the lock, right, the molecules here are the key. And so in this really kind of simple example, the S enantiomer does not have the right keys to put in the lock, but the R enantiomer does. And this has really huge implications in terms of drugs, right? If a drug is a mixture of enantiomers, you might run into some issues because only half the time it'll be effective. Or, who knows, maybe the other enantiomer will end up not being compatible to the enzyme in a really negative way. So this is how biologically chiral molecules are important, right? Remembering that enzymes are locks and molecules are keys, and we need the right set of keys in order to unlock the lock. Okay, so what we'll do during lecture is go through these examples, okay? Try to do these on your own beforehand, but assign R and S configuration for each of the chiral carbons in each of the following molecules.